In this video, I'm going to talk a little bit about what imaginary numbers are to kind of get a sense of how they fit into other kinds of numbers that we've thought about before. So let's start with the numbers we thought about kind of first in our educational career. We started thinking that numbers start with 1, 2, 3, 4, and so on. And when you were in early elementary school, we made sure that you knew all of these counting numbers, sometimes also called the natural numbers. And then as school went on, you had to learn about other kinds of numbers. Sometimes we had to talk about numbers that were 0 or even less than 0. And so we eventually had to deal with all of these numbers, which are called the integers, the ones that go on forever on either direction, and that are the whole numbers that one might count by and their negatives. But sometimes even this wasn't enough for the kinds of situations we found ourselves in. Sometimes we had to deal with things like several people were sharing a single pizza, and so we needed to represent ideas like 1/4 of that pizza or 1/2 of that pizza. So we took our integers and we created some new numbers between them to represent those fractions, those ratios. So now we'd have, right in here, we'd have 1/2, 1/4, 3/4, and so on. And we had similar numbers between each of these. And we included those rational numbers that we needed in order to do things like talk about fractional pieces of pizza and those kinds of situations. So because we had a situation where we needed a new kind of number, we invented even more numbers. And sometimes we have a property of numbers that only applies to certain kinds of numbers. Even and odd is an idea that only makes sense for integers. But we invented these extra rational numbers and filled them in. And then, somewhat later in math, we actually invented even more kinds of numbers. At some point, we also have the real numbers, which include all of our integers, all of our rational numbers, which also include the integers, because I could write any of these integers as a rational number. For example, 2 could be 2/1, and then it would be written as a ratio, as a rational number, 3/1, and so on. So I've extended the integers to include the rationals. And that let me do things like, deal with pizzas. It let me deal with a lot of different things. Somewhat later, we also learned about some irrational numbers, such as the square root of 2, which lives somewhere in here, the square root of 3, but not the square root of 4, because that would be 2. All of our square roots live here. We also have numbers like pi that are irrational numbers, numbers that we can't write as a ratio, but which are part of our real numbers. So the real numbers include all of my irrational numbers, like the square root of 2 or pi, all of my rational numbers, all of my numbers that can be written as a fraction of 2 integers, and then my integers, because all of them were also rationals. All of my rationals were also real. And when you were taught about the real numbers, you're kind of like, so is that all the numbers? Well, kind of. That's all the numbers that are going to be on our number line. I didn't draw a number line here, but I could have. I could have drawn this as a number line with 0 here, 1 here, 2 here, 3 here, and so on, as we did back in elementary school and middle school a lot to talk about numbers. So all of these numbers I can put in order on a number line. I know which side each of them is to each other. They all can line up in a line. And that would be our real number line. But just like I had to invent the square root of 2 when I was talking about squares and square roots, and I had to invent 1/2 when I was talking about fractions. There are some questions that we can ask in math where our answer isn't anywhere on this real number line. If I have a number and I square it, and my answer is -1, this isn't something that exists anywhere on this number line, because when I take the square root of both sides, I would get x here, and I would get the square root of -1 here. And because this doesn't make sense in our real number system, because if we think about our patterns with multiplication, if I take any positive number and multiply it by another positive number, I'm going to get a positive number. If I take 5 times 5, I'm going to get 25. It's going to be a positive number. If I take 7 times 7, I'm going to get 49. It's a positive number. And if I have a negative times a negative, I'm also going to get a positive number. -2 times -2 is +4. The only ways I can get a negative number when I multiply two numbers together is if the signs are different. And so as a result, we've kind of decided this whole idea doesn't make any sense because it doesn't fit anywhere in this pattern. But what if it did? Because there are questions where we've gotten answers like this. And in order to be able to do math on those questions, but what if it did? So, but what if this was a thing? And so this is how we extend our real number system with this new idea of imaginary numbers. We say, imagine it does work. And I'm going to decide that the square root of -1 will be represented by the symbol I. This isn't a variable. This is a symbol we're using to represent a number. So this is just like when I have something like the area of a circle is equal to pi r squared. That pi is a number. It's 3.14 some stuff. It's a number, not variable. This is the same thing. You may have also seen Euler's number E as a number, not a variable, depending on what math you've learned about before. And if not, during your study of logarithms, this will come up as another number that is a number, not a variable. It is not important for today. It is between 2 and 3 if you're curious, and that is a different lesson entirely. But so these are both examples of things that are numbers and not variables. And so this is a number. And we write it like this, just like I would write that the area of some circle or other might be, I don't know, 9 pi. I might write that some number is 9i if it were 9 times the square root of -1. So that's what an imaginary number is. And where this comes in handy a lot is with quadratics. So if I have something where I have an x squared term and an x term and a constant term, then we end up with some square roots, and sometimes they're negative, and that's one of the places this will come up. But for now, this is a new number, and it doesn't go on our number line. It goes on a completely different axis here, where we would have an imaginary axis and a real axis for our complex numbers. But for now, that's what I is. It's just the square root of -1, and that's because it's an imaginary number.